yeah, we're just feel fortunate to be a part of it. Anyways, yeah, Sturdivant's would also like to thank you guys for watching and continuing your education. It's such a key component for us to all stay safe out there. And for all you watching, if you come on into Sturdivant's at our Main Street store, we've got 30% off contour skins. If anybody needs some new skins, just mention that you watch Digging Deeper and we'll get you taken care of 30% off some contour skins. Anyways, thanks to Ethan and Chris for doing this. Look forward to watching.
Awesome. Thanks a ton, Ulin. Thanks again for hosting this tonight and for helping out on the board. It's awesome to have you. As we get rolling into the presentation here, just wanted to remind you guys that we definitely encourage questions. It's awesome to make these more interactive. And so yeah, don't worry about interrupting. I'm sure Ethan, when the time's right, would love to take a question. And there's a couple ways you can do that. You can quote, raise your hand. There's a little raise your hand button that you can see. And when there's kind of a break in Ethan's talk, we can basically hand the mic over to you. You can unmute yourself and then you can ask your question out loud. Alternatively, you can also type them into the chat box and we'll do our best to get those answered. So without further ado, I'm going to turn this over to Ethan. Take it away, Ethan.
All right. Thank you, guys. Appreciate it very much. And yeah, as a dad of 2 kids, I'm very used to being interrupted mid-thought. So by all means, please raise your hand and ask a question as we go along. So today I'd like to talk to you about winter storms, highlighting some winter storm patterns we experience here in the central Idaho mountains. We'll touch base on some basics of a winter storm, how that storm makes its way to Idaho, and how eventually it interacts with our topography. So we'll find out some of the snowiest and driest places of our forecast area, why certain weather patterns affect certain areas the way they do. And finally, we'll put it all together by comparing 2 very different types of storms, one that favors Banner Summit to our north and one that will favor the Wood River Valley. Since we'll be jumping around a lot geographically around the region, I just wanted to make sure everybody was acquainted with where we're talking about here. So the first thing we'll do is just a quick terrain overview of the different mountain ranges in our area, which should be helpful for some of you that are watching potentially outside of the forecast area. So here we are in central Idaho. Those shaded polygons are our forecast zones. We have 4 of them. Zooming in a little bit closer and moving from north to south, we'll just kind of identify some of the mountain ranges that we'll be talking about today. What I think is really unique and amazing about this area here we have in central Idaho, our backyard, is the diversity of mountain ranges and the way they all crisscross and come in from different angles. So it's a really interesting area geographically, and it has a really interesting effect on our overall weather patterns. To the north, we have the mountains near Banner Summit. You can see running down the center between these shaded areas here is Highway 75. So we have Bellevue at the bottom. We have Galena Summit here in the middle. We have Stanley, and then on up to Banner Summit in the north. We have the Sawtooth Mountains to the west of Stanley. The White Clouds to the east of Stanley. The Western Smokies, which some might confuse some people, which is kind of a blob of mountains that's a little bit further west and south of Galena Summit than most people usually travel from this side, but is a little bit easier accessed from the Soldier Mountain side. Then we have the Smoky Crest, which essentially extends south directly from Galena Summit on down through Baker Creek and eventually Dollarhide Summit. We have the Boulder Mountains, which are above Galena Lodge there on your way up to Galena Pass. The Pioneers, which are just straight east of Ketchum and Haley. And the Soldier Mountains, which are kind of northwest of Fairfield. So we have a lot of crisscrossing mountain ranges, which makes for some interesting topographical effects on our weather. So we're going to start it off right out the gate with a fun fact, but it's also going to be one that I'm going to poll you guys on to start. So I'm going to, or Chris is going to launch a poll for us here. to see which weather station is the snowiest. And that poll should pop up on your screen there. Your choices are going to be Trail Creek Summit, which is going to be just east of Sun Valley. Galena Pass, which everybody that lives anywhere around here is pretty familiar with, the high point between the Stanley Basin and the Wood River Valley. Banner Summit up to our north, if you're driving from Stanley on down to Loman. Vienna Mine, which some of you might not be as familiar with, which is the headwaters of Smiley Creek, kind of southwest of Galena Pass. And Dollarhide Summit, if you were to drive directly west out of Ketchum, you'd eventually, the high point you'd cross over before heading down toward the Soldiers in Fairfield would be Dollarhide Summit. So we'll go ahead and leave that poll open for just another minute here, and then we'll see the results. Okay, so it looks like the overwhelming favorite here was Banner Summit, followed closely by, well, not so closely really, by Vienna Mine. Galena Pass gets an honorable mention in third, and nobody bit on Trail Creek or Dollarhide. Interesting. Okay, we can go ahead and close that poll, and we'll find out what the answer is. Those of you who voted for Vienna Mine, you are correct. So the number I've displayed here on the screen is the snow water equivalent. So if you took a foot of snow and you let it fall into a pail and then brought that pail inside and let it melt into water, that's the snow water equivalent. So really it's measuring the moisture in a storm, the total precipitation in a storm. And it's probably the most unbiased way to track overall snowfall in the winter season. So Vienna Mine gets 35 inches of snow water equivalent a year, which is over 400 inches of an average density snowfall, which is pretty remarkable. Second place is Banner. You'll notice that it's a little bit lower, actually quite a bit lower in overall snow totals than Vienna Mine. Remember, I didn't say necessarily the snowiest place, but the snowiest weather station. There are some obvious downsides to the Banner Summit weather station as compared to Vienna Mine, one of which is that it's almost 2,000 feet lower. So some of those events that might have fallen as rain in Banner in early or late seasons could have fallen as snow in Vienna Mine. So that does skew things slightly. I'd put them relatively on equal footing though. So if you guessed Banner, I'll give it to you. One that I don't think a lot of people kind of saw coming, except maybe Ulan at the beginning when we were just warming up for this presentation, was Dollarhide Summit as the dark horse, as he put it. And it's not very far behind Banner, which might surprise a lot of you guys. Galena is a little bit less than Dollarhide, and then Trail Creek is less than that. Another way to look at this is this plot here. Actually, sorry, we're just zooming out a little bit to show kind of the overall forecast area, not just those 5 stations, but including a bit more into this calculus here. So the number one actually in our general region, which actually happens to fall just outside of our Banner Summit area, is the Deadwood Reservoir, or Deadwood Summit, which is just north of Deadwood Reservoir, kind of halfway between Cascade Lake and Cape Horn, with a whopping 43.7 inches of snow water equivalent, which is almost double that of Banner, which is really impressive. Right behind that is our favorite to always look at as a big storm is coming in on West Flow, which is Trinity Mountain, and that's just northwest of Pine. These two are outside of our forecast area, which is why they weren't included. Then Vienna comes in, and that's the top weather station for our particular forecast area at 35.3. Atlanta Summit near the town of Atlanta out there is at about 30 inches. One that kind of surprised me was Moores Creek Summit at 30 inches, which is quite a bit more, which is quite a bit more than I was expecting out in that general area of Moores Creek. Behind that is Banner Summit. And then we have Dollarhide Summit. And yeah, as you can see, there's kind of a pretty heavy skew to the west side of the map. So kind of drawing your attention to the east side, again, here's Highway 75. You notice some of these other snow totals out in the Pioneers, only about 20 inches here, 21 inches at Galena Pass, and less while we're talking 20 to 30 or even 40 inches or more on the west side of the highway. So we're going to talk a little bit more about what drives that big difference in overall snowfall changes. Another way to look at this is to look at it by, on average, these locations will hit a yearly maximum depth of, and then fill in the blank. So on the, now what we're looking at is actually snow depth, not snow water equivalent. So these are 30-year averages again, just like the last snow water equivalent plots. But we're talking about the deepest snow on average that location will see during the winter. And the winter this time is actually Trinity, which has an average, which will at some point during the winter hit over 100 inches of snowfall on the ground, measured snowfall on the ground each winter, which is pretty remarkable. Not far behind it is Vienna. And then again, which is Vienna is right here. Then we've got Deadwood again up to the north, or yeah. So again, we're talking about the deepest snow in the western side of our forecast area. So a natural question to ask is why this is the case. To answer that, it kind of helps to have a little bit better understanding of the basics of a winter storm. And that's what we'll get into next. In the simplest terms, winter storms begin with moist air rising up into a cold atmosphere. There are three main ingredients of a winter storm. The first thing is you need cold air. Obviously, it needs to be below freezing, but one thing that I think will surprise a lot of folks is how deep that layer of cold air needs to be, and actually how cold that layer of cold air needs to be. Probably a lot colder than most of you think. The second thing you need is moisture. Just like this little cup of water here, that is liquid water in the cup, has water vapor above the cup. If you warm that cup of water up, more of these little water vapor molecules will escape the surface and float around above. And it's this water vapor that's floating above the liquid water that is the fuel for our winter storms. The major sources of that water vapor, at least for our weather purposes, are going to be oceans. But regionally, we can see that water vapor coming from lakes, like the Great Lakes or the Great Salt Lake, and vegetation if it's the summertime, but we're talking winter storms here. The final thing that we need is lift. And this little image here shows air blowing off of an ocean up a mountainside, and that mountainside is providing a physical barrier that's forcing that air up into the atmosphere. So that is the form of lift due to orographics or mountain features. Other things that can cause lift in the atmosphere are weather fronts, and we'll touch on those as well. So the atmosphere, much like the snowpack, has layers. It has layers of warm air and cold air. It has layers of dry air and moist air. And in this plot, what you're looking at is elevation on the y-axis and temperature on the x-axis. 32 degrees Fahrenheit or freezing is right here. So it's getting colder as you move this direction, warmer as you move this direction, and this is going up in the atmosphere. So what we have here is an atmospheric profile that's plotted in green. So the temperature of the atmosphere is increasing with height, and then it's starting to decrease with height. And we know that it can increase with height and decrease with height. It doesn't just get colder as you go higher up into the atmosphere. This temperature profile would allow for snow to fall. We've got a little cloud, snowfall all the way down to the ground. And the reason being is the temperature in the cloud is below freezing. It's somewhere around 23 degrees. The temperature in the atmosphere below the cloud is also below freezing, although it does warm to near freezing right here. It stays below freezing, so it's going to keep our snowflakes pristine without melting them. And then it's going to allow that snowfall to come all the way down to the surface. If you warm that layer in the center of the atmosphere just slightly so that it pokes above freezing here, you're going to change the entire equation. Instead of snow, you're going to form sleet. Again, you're going to start as snowflakes. It's going to fall into a shallow, warm layer that's going to melt those snowflakes into liquid precipitation. And then it's going to fall through a cold layer again that's going to refreeze those from a liquid water drop, essentially into an ice pellet, which we call sleet. The third type of winter precipitation, and why, again, it matters to have this deep layer of cold air, not just cold air near the surface, is freezing rain. We can again start as snowfall high in the atmosphere, which even in mid-latitude summer months, most precipitation that hits the ground as rain actually starts at snow. So there's another little fun fact for you. It's actually snowing in July quite often around here. It just falls to the surface as rain. It's starting off as snowfall, falls through a deeper layer of warm air this time, doesn't have a chance to refreeze into sleet before it hits the ground. So it hits the ground as liquid water and then freezes on impact, which is what we call freezing rain. Fun fact number 2, man, we're just throwing them out there today. Liquid water can exist down to around -40 degrees Fahrenheit before it freezes. If you're familiar with this concept, it's kind of a fun one to bust out at a gathering if you haven't explained it to somebody who doesn't know yet. So pure water does not freeze at 32 degrees Fahrenheit or 0 C. It will only freeze if it has an ice nuclei. So at the center of all these snowflakes that I have this beautiful picture of here on the right-hand side is a tiny, tiny solid that's only a few microns across. And those ice nuclei look molecularly a lot like ice. And obviously a tiny, tiny, tiny fragment of ice would be the perfect ice nuclei. And in fact, at the center of a lot of these, there might just be a small solid particle of ice, but there are many others. Clay or crustal materials happen to be ones that look molecularly similar to the molecular structure of ice and are preferential for ice nuclei, but other materials work as well. And what's interesting is that the colder the cloud temperature is, the more different types of ice nuclei you can activate. So while the ones like other pieces of ice and clay are activated first, others are activated as the cloud gets colder. So when I say that cold temperatures matter for snowstorms, you might be thinking, well, yeah, of course it does. But some things to keep in mind are that even at temperatures near 25 degrees Fahrenheit within the cloud, there's a very small chance of ice actually being in that cloud. You have to reduce the temperature of that cloud down to about 14 degrees Fahrenheit to get a 60% chance of ice, 10 degrees Fahrenheit to get a 70% chance of ice, and 5 degrees Fahrenheit to get a 90% chance of ice. So in order to say almost without question that there's ice in a cloud, it needs to be almost 0 degrees in that cloud in order to have enough available ice nuclei to change the liquid water to what we call glaciate the cloud from liquid, super cooled liquid water to ice. And in reality, most clouds up in the atmosphere are what we call mixed phase clouds. They have both super cooled water droplets that just don't have an ice nuclei available alongside ice particles. And it's actually the coexistence of both of those in one single cloud that drives a lot of the ice crystal growth processes that create these beautiful snowflakes and the really, really high vapor density gradients that create really rapid growth of snow crystals and snowfall. So to start and maintain a good snowstorm, you don't just need a little cloud to be near freezing. You need a deep layer of the atmosphere to be well below freezing. So where does all this cold air and moisture come from? Here in Idaho, the main source of moisture feeding the storms is the Pacific Ocean. This map illustrates a pretty important basic concept of meteorology, which is the air mass. So essentially, these air masses have been named because they have characteristics that we see influencing weather day in and day out. A particular air mass sitting over will take on the characteristics of what it sits over. So for instance, the continental polar air mass, which we can see right here over the interior of Canada, will be drier than that of the maritime polar air mass, simply because the air that's sitting over the ocean is going to be taking on a lot more water vapor available to it from the ocean than this continental drier air mass over central Canada. Also, as you'd expect, a storm dropping down from the interior of Canada is going to be colder than a storm dropping down from the Gulf of Alaska. So when we hear about Arctic outbreaks or some, cold snaps and things like that, there's almost always, well, there is always some sort of Arctic or polar air sinking down in from interior Canada. Maritime air, on the other hand, of course, the ocean, as long as it's not frozen over, is going to be relatively warm. So we're going to have warmer and moist air coming in off the ocean, drier and colder air coming in out of interior Canada. So this effect can actually be seen on smaller scales as well, which is one of the neat things of meteorology. If you're not familiar with a lake effect snowstorm, if you live down near the Great Salt Lake, you're probably pretty well versed in this. Or if you're along the Great Lakes of the Midwest, I'm sure even if you don't know what's going on, you see the snowfall and have to deal with it on a regular basis. But essentially what's happening here is we have a relatively warm body of water, let's just say the Great Salt Lake, and we have cold air moving in from the north. That water is providing heat and moisture, which starts to create some clouds. Those clouds grow bigger and bigger. And of course, when we hit a certain depth, it's going to start snowing. And eventually it's going to dump some heavy snowfall on the banks of the other side of the lake, particularly if there's a little bit of lift, some gradual rise on the other side of the lake. This video here is of the Great Lakes, and it's a winter radar showing some lake effect snowstorms. And it's really cool. You can see the wind coming in from the west and the northwest, and down here as well, coming in from the southwest. And what's interesting is that lake effect snow is going to be more intense when the direction of the wind lines up with the orientation of the lake. So for a good snowstorm in Chicago, in Lake Michigan, we're going to have to kind of ignore the pattern of snow, of wind rather, and that's going to hit down here on the south end. If we're looking for good snow in Buffalo, we're going to want this kind of southwest fetch. So in this particular storm, it's probably just absolutely nuking in Buffalo. There's also something called the Tug Plateau out here on this side, which is kind of an elevated bit of land that's going to help lift and condense more of that water out on the New York side. So the next thing we'll talk about, and I alluded to there briefly, is lifting mechanisms. So we've talked about where the moisture comes from, and that's going to be our ocean primarily for us. We talked about the cold air, where that comes from, which can be either maritime in origin or continental, but it's coming down from the north in general. And the next thing we'll talk about is lifting mechanisms. And we'll touch on these pretty quickly. Frontal lift. Both warm fronts and cold fronts emanate from the center of low pressure systems. A warm front is defined as the leading edge of a warm mass of air. So warm fronts are delineated here or denoted here by this line with red half circles. And what it means is that warm air is headed your direction. Warm air is behind that warm front, and the warm front is the line between those two. When warmer air arrives, it runs up and over the more dense, cooler air at the surface, which provides gradual, slow lift. So if we look at this diagram on the right-hand side, the air is blowing from left to right. The warm front will kind of be right here in this line. And that warm air is riding a ramp up and over the cooler air that's at the surface. And the effect that you'll see when a warm front is coming is oftentimes high cirrus clouds, very thin, wispy clouds, really, really high up in the atmosphere. And you're seeing these cirrus clouds way up ahead of a warm front. As that warm front gets closer, those clouds start to thicken because that layer of warm air is starting to get thicker. And you might start to see some drizzle or snowfall. Most oftentimes, because this is such a long, this can be several kilometers or several miles long, this long ramp leading up to it. This precipitation is usually pretty light and it isn't very heavy until the front is kind of just about to pass. So it's kind of a slow buildup. Sometimes if it starts to snow as the warm front passes, it can erode out this colder air near the surface. And a lot of times when we have warm fronts, we'll start as snow, particularly in the spring in the Wood River Valley. And then you'll see as that warm air starts to erode this colder air, we'll see rain lines start to creep up to the valley and even higher up to the mountain passes. A cold front, on the other hand, is just defined as the leading edge of an advancing sector of cold air. So it's denoted here by these blue triangles as it's moving across a weather map. And it acts much more as a wedge, which forces the warm air steeply into the atmosphere. So precipitation can begin abruptly, and it can be more localized and heavy. Instead of that gradual overrunning of warm over cool air, we have this colder air just shoving the warm air straight up real fast, creating a lot of lift and developing showery precipitation right along the cold front. It's also usually, as I mentioned, it's more localized. It's not as wide of a band of precip as the warm front might be. So we'll move quickly now into orographics, which is what I consider the main reason why our snow distribution is the way it is across central Idaho and really affects where it snows and where it doesn't, given the different flow patterns in our mountains. It also explains why it snows more over mountains than in the adjacent valleys. In its most simple form, orographic precipitation, just meaning precipitation caused by the mountains, occurs when a deep layer, remember it has to be deep, of sufficiently moist air is forced over a terrain feature. So in this image here, we just have air moving from, let's say, the west, and it's moving up and over this mountain range. As the air mass expands, as it rises, it's going to expand because it's finding itself in lower atmospheric pressure as it goes up in the atmosphere. So it begins to expand. As it expands, it cools. And as it cools, some of that water vapor begins to condense into liquid water droplets, which form a cloud that we can see. And then eventually, if it's deep enough and there's enough lift, it will form, and if there's enough moisture in the cloud, it will form precipitation. The precipitation is going to be focused on the top of the mountain and the windward side of the mountain. So this explains why there will be more snow. It could be below freezing in this entire image, but there will be more snow right along the mountain top than down in the valley bottoms. It also explains why there's more snow on the windward side than there is on the leeward side. Because as the air moves beyond this feature, the lift has been removed from the equation. It's now just kind of going straight, as well as some of the moisture has already precipitated out. And oftentimes what is the case is after it gets forced up, it then gets pushed back down. And the effect of getting pushed back down is going to condense that air mass, warming it up and drying it back out. So we call this side kind of the rain shadow. I lived on both sides of the Cascades growing up in Oregon, the wet west side and the dry east side. And if you just take a look at a satellite image of one side or the other of the Cascades, it really illustrates that point where it's green and fertile and wet on the west side, and it's high desert on the east side. This process by itself simple, stable upslope precipitation is actually pretty inefficient at creating precip on its own. Usually other processes have to be at work in order to get a good snowstorm going. So one way to enhance this type of orographic effect is the development of what we call a cedar feeder scenario. In this example, we have the same upslope cloud that we had in the first example, but we also have what we call a cedar cloud that's formed in the upper atmosphere above the orographic lifted capped cloud that's kind of sitting above this mountain range. The upper elevation clouds, remember, because they're likely to be colder, are going to contain more ice. If you have more ice up here, you're providing ice nuclei as it's falling into this moist layer right above the top of this mountain here, which is going to enhance the snowfall within this storm cloud. It's going to give it more ice nuclei as it comes in. So providing more ice nuclei will enhance the snowfall rates of this lower cloud as well, which is kind of a neat effect. Also, if we're just worried about snow water equivalent, some of the snowflakes falling from this upper cloud are going to sweep out water vapor, essentially get rime attached to them as they come down through the supercooled water that's existing in this cloud. So it can increase the overall water hitting the ground simply because these snowflakes are gathering more water through this cloud before they hit the ground at the bottom. This setup can produce snow in this lower cloud when it may not have been occurring otherwise. This could have just been a cap cloud with no precip falling, but you introduce this ice nuclei from above and all of a sudden it starts to glaciate and then it starts to snow underneath that cedar cloud. But if you really want high precipitation rates, you need some instability in the atmosphere. So by far, adding a little bit of instability into the atmosphere is how we get the heaviest snowfall rates. So just looking at this image, you can probably see the difference in the cloud shapes between the first, which were relatively flat clouds, to these ones that are much more puffy and vertical in nature. So if your mind is kind of going to thunderstorms, you're right. This type of tall convective cloud isn't as common in midwinter, but is quite common during spring storms. And they form when the rising air over the mountains cools more slowly than the air that is surrounding it. So as this parcel of air, let's just follow this line, as this parcel of air gets lifted up over this mountain, it's going to cool. But if it cools slower than the environment that it finds itself in, then it will be positively buoyant and it will continue to rise uncontrollably. One way to think about it is to think of a hot air balloon. The balloon rises when the air in the balloon is warmer than its surroundings. So too, if the air in this column of the atmosphere in this cloud is warmer than the snow adjacent to it on either side, it will continue to rise. And that's what causes these billowing cloud tops to continue to push higher and higher. And of course, the deeper the convection we have, the more room we have to develop precipitation, the more condensation that occurs, and the longer it takes for precip to fall through, the larger the precip can get. So overall, it's just going to enhance snowfall rates by having a little bit of instability in the atmosphere. Okay, I think we have a pretty good sense of a base level of knowledge to help us understand what's needed to create a winter storm. In our neck of the woods, the cold air is provided by the air masses that drop down from the north. The moisture is provided by the ocean, and the lift needed to condense that moisture out of the air is provided primarily by our mountains, but also by frontal passages. But there is one more big variable that's going to help us determine when and where these storms will occur and who will get the most snow. And that variable is the jet stream. The position of the jet stream and the areas of high and low pressure around them are what you can kind of think of as the steering current of the atmosphere that either keeps us high and dry or it simply just lines up the storms ready to hit us. Jet streams are relatively narrow bands of strong wind in the upper levels of the atmosphere. The winds blow from west to east in the jet stream, but the flow often shifts to the north and south. So we have these jet streams that circumnavigate the entire globe. We have the Pacific jet or the subtropical jet, the polar jet up here. And in the wintertime, our weather is primarily influenced by the polar jet stream right here. They generally are coming from the northwest and west, but you know, they have some up and down swings in them. That's going to really heavily influence our weather. The jet stream forms on boundaries between the hottest part of the atmosphere and the coldest. So where the temperature is changing the fastest is where the jet stream is going to set up. It's along that boundary of greatest change of temperature. So we have colder air to the north of the jet stream and warmer air to the south of the jet stream. And it's that interplay of that cold and warm air mass that's going to also create storms. So the jet stream is a good thing to look for if you're looking for the overall idea of where the storm track might be on a given day. This animation here is of the globe. If you can focus, here's the west coast of the United States right here. And the red colors are going to show rough positions of the jet stream. And this was created today, so this is current. And you can see the jet stream kind of coming down around here, and then it bulbs up over the west coast, and we're sitting right here, and then back down kind of past Idaho. And I'll show you the animation here. So again, these are streams of upper atmospheric wind, where the wind is going to be the greatest. And it's also the rough dividing line of where the coldest air and the warmest air is. Following the jet stream is also going to indicate where you're going to find our winter storms originating. And I'll explain that here in a second. So kind of an idealized image of the jet stream here in blue. And the main features I want to point out on this are areas of high pressure and areas of low pressure. So right now we are under a bulb of high pressure. If we kind of took this pattern and shifted it over to the west coast, we're sitting under one of these bulbs of high pressure. And what does that actually mean? High pressure means that there is more air above our heads right now than there would be if we had low pressure above our heads right now. There's literally more force of the weight of the atmosphere above our head during high pressure than there is in low pressure, because that air is converging in the upper atmosphere and sinking down to the surface, and it's packing that column of air above our heads. And that sinking motion is going to is going to compress the air as it comes down, which is going to heat it up and dry it out, which is the basics behind why we have mild, warmer weather under a high pressure ridge than a low pressure ridge. Conversely, under a low pressure ridge, we're going to have rising air. We're going to have air converging at the surface, but then it's going to be lifted into the atmosphere and then diverging up in the upper atmosphere. And another way to look at it is this. Here's our jet stream. We have to remember that we're talking about something that isn't two-dimensional. We're talking about multiple different heights in the atmosphere. So this upper one up here is really, really high in the atmosphere. And this one down here is at the Earth's surface, okay? When we have a ridge like this, we have an upper level tropospheric ridge is what we call it. But there's high pressure at the surface because there's sinking air, which I just explained. Once that gets to the surface, it diverges, it goes out in all directions here. The opposite is going to be this low pressure trough. And when we're looking for storms, because we don't want warm sinking air, we want cooler rising air, we're looking for this low pressure system, either at the surface or looking for this pattern of troughing in the upper atmosphere. So right in front of these troughs, if you were to look and see an upper air map and find one of these troughs, you would find a co-located low pressure system at the surface. And the reason is because we have diverging air here out of this column, which means that we need to have converging air here at the bottom of the column. And that upward motion is going to provide our lift that's going to produce our low pressure cyclones and our winter storms. So now we'll dive into a few local patterns. Everyone watching kind of intuitively knows that the majority of our storms arrive from the west and the northwest. This image shows the average position of the jet stream in the winter, and it backs up what we all assume. Storms from the Gulf of Alaska follow the prevailing wind roughly along the path of the jet stream until they arrive in Idaho. So let's recall our map of the snowiest mountain weather stations from the beginning of the talk. As a general trend, our snowiest locations are northwest and west of sides of Highway 75. So I don't think that it's an oversimplification to simply just draw a line down the valleys from Stanley to Galena Summit and on down into the Wood River Valley and simply say that it is snowier on average to the west and less snowy on average to the east and south. And a big reason for this is going to be this shadowing effect that we talked about with orographics. If our prevailing storms are always coming in from the northwest, the mountains that are going to get that initial benefit of the lift are going to be the mountains in the north and west side of our forecast area. After they pass through, whatever remnants are left is what's going to fall on our less snowy side of the highway, which is the Pioneer Mountains, the boulders and the white clouds. And just looking at these overall SWE numbers on average, the data bears this out, where we have anywhere from 50 to 75% of the snowfall on this side as we do on this side of the highway. This was the placement of the jet stream and a surface low pressure system on January 5th. This was of this year. This was the day 2 of a 5-day storm that we had that absolutely hammered the northern and western portions of the forecast area. Multiple low pressure systems formed in the Gulf of Alaska and rode the jet stream down into our area. And if the jet stream stays near, meaning that it doesn't move off away from Idaho, it's not uncommon for 2 or more storms to impact an area over the course of 3 to 4 days, which is exactly what happened earlier this year. And again, this was a storm coming in on west and northwest flow with the jet stream oriented approximately as I drew it in here. And what was that? What was the effect? What did we see? Because these storms arrived on northwest flow, we saw a big bias of heavier snowfall in the northern and western reaches of the forecast area. So here's a plot showing the storm totals at Baldy in blue and Vienna Mine in orange throughout the event, starting with day 1 on through day 5. So obviously we can tell Vienna Mine here, they started off with a little bit of snow, both pretty close on day 1. And then we just steadily climbed at Vienna Mine with more and more and more and more snowfall as those storms arrived on northwest flow. While Baldy, and this goes not just on Baldy, but also the boulders and the Pioneers, just didn't get the same amount of snowfall because they were, and why, what is the main reason for this big discrepancy? It's that the storms arrived from the west and northwest. And we saw in the section about orographics that the heaviest precipitation on the windward side of the range as the air is lifted. And there simply just wasn't as much precipitation available, essentially a miniature rain shadow for Baldy and the south and eastern mountains. So although the northern and western mountains receive more frequent snowfall because it is the average storm track, the southern mountains can see some of our biggest storms. So never fear. For Baldy and the Wood River Valley to really get hammered, we need to shift the flow to the south. By doing that, we remove all of the upstream obstacles that steal all of the good lift away from our storms as they arrive. Instead, moisture can kind of stream up through here in southeastern Oregon and southwestern Idaho and approach our region in the southern mountains, whether that's over by Fairfield and the Soldiers or in the Wood River Valley, relatively unimpeded. For those conditions to develop, we just need the jet stream to drop to a lot further to the south to allow these storms to approach from this direction instead of coming in from this direction, which doesn't happen as often. Under some conditions, we can get a deep low pressure system or a bomb cyclone that forms off of the Oregon and Northern California coast. So here you can kind of see the jet stream moving down and this really huge cyclone starting to form off the coast of Washington, it looks like, or Oregon in this particular one. These huge storms can interact with and intensify long plumes of moisture that are emanating from the tropics. So one benefit when the jet stream dips down instead of staying high to our north is that it pushes these big cyclones. Here's one forming out here in the Pacific and then moving towards us. It allows these storms to be further south, which gives them a higher likelihood that they can impact with this larger moisture source, which is the tropical Pacific, instead of kind of the mid-latitude Pacific. Because if you remember back to our source of moisture discussion, if you have warmer water, there's more water vapor available above warmer water to provide fuel for these storms if they can tap into tropical moisture as opposed to colder ocean temperatures, which have less water vapor available. Another benefit is that the water starts low in the atmosphere with these. And it doesn't run over as many barriers before it hits us. Obviously, if it tries to go up and over the Sierra, that can sap a lot of the energy. But we have a pathway for these atmospheric river events to kind of sneak through right along the Northern California coast and wrap up into our valley here, and we can absolutely get hammered by those storms. So, question: what were all of you doing 1 year ago today? If you were me and getting ready to forecast in the morning, you were anticipating one of the more memorable atmospheric river events to slam into the Wood River Valley in a number of years. This plot shows what can happen when the flow is right, which means it's coming from the southwest, southeast, and an atmospheric river develops, like we were just speaking of. This 4-day storm inverts, kind of flips the scales on what we just talked about on a northwest flow storm. Here we are showing Baldy in blue and Banner Summit, one of our traditionally snowier areas, in orange. This 4-day storm dropped 47 inches of snow at Baldy in just 4 days, 41 of which fell in just 48 hours, which was this period right here. So we can get really big storms in the southern mountains. It just depends on which direction they're coming from. And for us, we need that to be more of a southerly flow in general. So some takeaways, and then I'll give you one more fun fact before I take some questions. Winter storms really are just moisture from the ocean, deep cold air, plus lift. And our lift, the most important one, is going to be the mountains. Our snowiest mountains are the west slopes of Banner Summit, the Sawtooths, and the Western Smokies. And the reasoning behind that is they have great orographics, meaning they have great lift. They are the first big bumps that the stream of moisture hits once they leave the Pacific. Second, they have a minimal rain shower they have a minimal rain shadow rather, because they are really the first big bumps to be hit before moving further inland. And the third reason is that it is also just the most consistent or the most common storm track. If you recall back to the average position of the jet stream, it's generally slanted from northwest to southeast across the area. So that's just the average flow for our neck of the woods. The outliers would be southwest flow. And if you live southwest or south flow, and if you live in the Wood River Valley, the words atmospheric river really should be music to your ears, because you know that we're going to be getting southwest or south flow, and the potential is there for us to get hammered with heavy snowfall here in the Wood River Valley. Our final fun fact, if you've ever wondered how we came up with these funny shapes for our different forecast areas, the forecast zones encompass areas with similar snowpacks due to common weather, terrain, and elevation. So we segment these into the different areas that we did. And one of the big reasons that they're shaped the way they are and the boundaries are where they are is because of the primary weather patterns that are going to shape the snowpack in similar ways. Our southern mountains are usually going to benefit from the same weather. Our western mountains are usually going to benefit from the same weather. And we make this distinction here between Banner Summit and the Sawtooth, which is probably more terrain driven than anything else, because they're both going to be pretty snowy. But obviously the mountains in the Sawtooth are much different scale than the mountains around Banner Summit. This zone, kind of oddly shaped, but all the way across the east, the eastern mountains, is shaped the way it is because it's the driest part of our zone. So a little known fact that there is some method to the madness of why we shape the forecast zones the way they are. I just want to point you to some resources. The Sawtooth Avalanche Center has a daily mountain weather forecast. We also have a weather station map, which is going to show all the weather stations in the area, so you can check in on them daily. And something that we've worked hard to continually put effort into each year is this weather tools page. Here you'll find links to weather stations and webcams. You'll find links to satellite and radar and model data. There's even little tutorials in there that we found on the web that explain the different satellites, explain the different models. We've tried to add those in there when we find them. And some other links to some kind of online weather schools that walk you through some really cool talks similar to this one, and then as in-depth as you want to get. So check those out. The webpage that I just continually come back to is the one from the College of DuPage. It has surface analysis plots that show you where the warm and cold fronts are. It has satellite and radar links, and it has weather models. And I think if I was to just pick a one-stop shop for weather nerdery, it would probably be this page here. So be sure to check them out. Here are my references, and I hope you've learned some basics about winter storms, picked up a fun fact or two along the way that you didn't know before, or at least connected some dots that may have been in the back of your mind. So thank you very much for your time, and I'm happy to take any questions that you guys have.
Just a reminder, if you have a question, you can click that raise your hand button and ask it live, and you can also type them into the Q&A box. So fire away. Ethan, while we're waiting for people to gather their thoughts, one question, actually maybe I'll hold off on that. Question just came in. An anonymous asker says, how common are atmospheric river events? Are they occurring more recently and in the past, or is it a consistent occurrence? That's a great question.
Yeah, I think it's interesting. The actual number of atmospheric river events really hasn't changed. And on average, you're going to be looking at anywhere from, and if we're talking just specifically to impact the Wood River Valley, we're going to have maybe three-ish on average a winter. If you're talking about landfalling atmospheric rivers, so the total number of atmospheric rivers that's hitting the west coast of the United States, it can be anywhere from like 50 to 70 on average. So there's actually quite a few, but not all of them end up, because they're pretty narrow features in the atmosphere. Not all of them end up crossing our path, obviously, and some of them just simply don't penetrate far enough inland to reach us. but I haven't seen any patterns of them becoming more or less common in recent years. But our data set is also fairly limited on that as far as time scale goes.
Awesome. That was a good question. TWW asks, do you expect that we'll get a snowy February? I've heard that the Northwest typically has a snow drought in midwinter.
Yeah, I mean, I'm not much one for kind of longer climate predictions. I guess I'd probably defer to the CPC for that, the Climate Prediction Center. And they have plots that show, whether they think it'll be cooler than normal in the 8 to 10 day range, or wetter than normal in the 8 to 10 day range. And then they also go out to the month and 3-month range outlooks and those sorts of things. Rather than looking at that, I try to encourage people to just look at maybe the 2-week trend and where the jet stream is. So again, are we going to be under regions of high pressure or under regions of low pressure? And if you just take a look really quickly, I guess I can pull it up. If you take a look, can you still see my screen there?
We can, yeah.
Okay. This is the upper air pattern. This is 500 millibars, and this is roughly the jet stream right here that we're looking at. And this is at that College of DuPage website. And we can get out, 10 or more days here just by scrolling forward. I think we can go to February 11th. So this gives us half of the month of February. And right now we're under this ridge, which is why we're dry. And if you move this forward in time, that ridge seems to persist for some time, unfortunately. There is a little break in that ridge right here, which is going to give us some of that weather on Monday. A few inches of snow is all it looks like. But then that ridge kind of builds back in. A lot of times if our flow is coming straight down from the north like this, or we're on the back edge of this ridge, we might get some small amounts of snow, but really this pattern to me is not looking favorable for snow. What we need is to turn it more zonal, which means that the jet stream's kind of coming more right at us than it is, like kind of about right there. So maybe we're talking, this is February 9th and forward, we might be getting a little bit more precip coming. But that's, rather than make a sweeping prediction about a whole month, I kind of like to just focus on where the jet stream is, because that's where the storms are. And so that's what I'd encourage you to look into.
All right, looks like we have a live question here from Annie and/or Toria. Let's see, I'm gonna allow them to talk. You can unmute yourself.
Hi there. Can you all hear?
We can hear.
Thanks for the talk, Ethan. And I was curious, I know you all don't forecast for the Lost Rivers, but just kind of in what you were talking about, would an atmospheric river affect that zone the same? And I guess my assumption is that it would almost be drier for any like northwest storm. I was just curious if you had thoughts on that.
Yeah, I don't pay as close attention, obviously, to the Lost River as I do in our forecast area. But generally speaking, I do know that the overall snowpack in the Lost Rivers is much more reminiscent of our eastern mountain zones over here than it is the wetter west side. And as far as a northwest flow goes, I don't know how they're not oriented in the correct orientation to really benefit from a northwest flow as much, because they're kind of northwest to southeast oriented. So the upslope will definitely be limited there. But that's about all I can say as far as northwest storms go. One thing that it might benefit from is just being a bit further east. And a lot of times when we get these blocking high pressures, we get these high pressures that kind of set up and come down right along the Montana border right here. And it could be snowing, sometimes even heavily out here on the Montana border, and we're still under the bubble of high pressure. So there's the potential that sometimes they could be getting clipped a little bit more than we are. But the storm track that really the Lost Rivers, I would imagine, benefit from the most is an atmospheric river or a cutoff low. It's getting to be a little bit inland for an atmospheric river because it's going to have to get through us and the Pioneers. It's very rare to have an atmospheric river kind of curl in from the southeast. It's usually southwest or south at its steepest angle. But a cutoff low, which is similar, can be when the jet stream kind of bulbs down over California, and then you see this low pressure circulation kind of float almost aimlessly over here over central Nevada, and the jet stream reestablishes itself way up here. And so this kind of ambling cutoff low tends to start to peter out and drift into southern Idaho right here. And when it does, because it's so slow moving and it just kind of sits here and churns, it pushes moisture up to the south, which can obviously benefit us, but can also provide wraparound moisture, like moisture actually circulating all the way in and then coming in from the east, that I'm sure would reach a little bit further into the Lost Rivers than any other type of storm.
Awesome. That's great info.
And there's a strange lack of weather stations in the Lost River region in general. I think there's only one kind of up on Pass Creek that I know of that's very useful in that area. So it's kind of unfortunate for data collection.
Ethan, there's a couple of questions in the Q&A, and I'm going to combine two of these. I think they're kind of related, but they're trying to bring back kind of the weather conditions to our avalanche conditions, which is what we're typically most interested in. But one person asks, how will this long dry spell without snow affect our snowpack? And then Emily Kaufman asks, if we were to receive a significant storm, how would the severely wind and sun affected surfaces we have currently impact stability? So yeah, how does this dry spell basically, how is this dry spell going to leave us when we get snow, and maybe specifically with those wind and sun affected slopes?
Yeah, those are great questions. And I guess I can approach it from two different ends of the spectrum. If you want a super stable snowpack, you want it to snow a little bit often, like a little bit today, a little bit tomorrow, a little bit the next day. If you want a snowpack that's going to be riddled with weak layers and weak snow, and then slabs on top, and then weak snow, you basically have to have the weather pattern that we just had, which is these long dry spells. So the answer to that is we're more on the leaning towards a snowpack that it could be potentially unstable with a bunch of loading coming forward rather than stable. And the reason that is as you pointed out, these dry spells allow the sun to go to work on south facing slopes, which can produce crusts. And then also on other kind of colder aspects, you've got heavy colder aspects and lower elevations because of our inversion. We have some heavy faceting going on and surface ore growth going on. So we're developing a nice weak layer at the surface on a lot of slopes that were, if we bury it and we bury it quickly, would spike the avalanche danger almost certainly.
And then Emily had asked kind of specifically about like sun and wind affected slopes.
Yeah, and how they might, so I guess the wind on one hand would kind of strip some of that snow away entirely on some slopes, which could actually provide really good stability if you're talking about some of the slopes down here around the Wood River foothills that are almost completely back down to dirt. And then, the sun can kind of create a kind of a mix of different crusts, which could bond well or could not, depending on kind of the character of the crust itself. Was that kind of what you were headed toward, Chris?
I think that was probably what she was getting at, but yeah, I mean, seems like long story short, after a dry spell, when we start getting snow, any slope's going to be suspect, but probably the worst of the worst is going to be those shady places where the skiing and riding is still good right now. where the snow is soft and which is actually faceted.
Right, yeah, and it'll be highly variable, obviously, as well. Yeah.
Ethan, I had a question, and this might pertain to the Lost Rivers a little bit, but sometimes you hear people talk about like a wraparound pattern. What is
Mhm.
that referring to?
Yeah, so wraparound moisture, I think I have,
It
I
seems
kind
like
of go back up.
that's a pattern you sometimes hear about hitting the Lost Rivers.
Yeah, so a wraparound moisture is really moisture that's associated with an occluded front. So when the cold front catches up to and overtakes the warm front, they kind of create this hybrid. And they continue, as you can see, this cyclone is continuing to kind of wrap itself up into a little spiral here at the middle. It's drawing in moisture from above, and literally it's swirling its way all the way in to the center of the cyclone. And so actually a kind of a classic example of wraparound moisture is a cutoff low that affects the Four Corners region of Colorado. So when we talk about an upslope, see if I can bring my, and this would be the same mechanism for kind of curling moisture into these areas that are harder to get to, that would normally be blocked by all the mountains leading from the prevailing wind side. We get these same storms when one of those cutoff lows that I was talking about over Nevada creates wraparound moisture for the Lost Rivers. Sometimes those can plunge way down here into the desert. And when they do, they start to peter out right in this region in the Four Corners. We just called them Four Corners lows. And when they're centered over the Four Corners, the moisture is actually coming around and coming in from the east and then hitting the front side of the Front Range of Colorado. So we can get, I'm thinking of one storm in particular. One of our forecasters, when I was working down in Colorado, called for anywhere from 1 to 48 inches of snow in the Front Range. And he nailed the forecast because there were areas outside of Fort Collins that had this wraparound moisture that got upwards of 48 inches of snow, and then areas just inland that, this is a very specific weather pattern only benefiting the upslope side of the Front Range of Colorado, that just a little ways inland there was essentially no snow. So that's these cutoff lows, and by cutoff we just mean it's cut off from the jet stream. Any jet stream support has retreated back to the north, and it's just kind of an ambling, slow moving, churning storm that eventually will fill itself in and die. But before it does that, it provides a lot of moisture coming in from the east and even northeast, which is an uncommon angle.
Awesome. Thanks, Ethan. Let's see, we have a question here. What's your favorite tool for tracking weather and predicting storms? You touched on, a bunch of the DuPage tools you like, but anything you want to add to that?
Yeah, I can just show you. I mean, this is what some of the weather model stuff in this page would look like. You can also hit satellites and radar, and you can pick up, sorry, my internet's going a little slow here, but you can see satellite imagery, and you can play those, you can play loops over this kind of terrain. So I really like the College of DuPage site. The other one that I like, if you're just looking for a particular spot, is just actually called Spot Weather, or spotwx.com. And I actually have it, you can save some favorite spots, or you can just ask it to tell you the weather where you're at. I like to kind of save a few spots. If we just click on, let's just say Stanley, it'll populate this list down here with all the different models of that you can look at that are resolved on Stanley. So each of these boxes is the domain that model is good for, and it tells you how long they're good for, 2 days up to 10 days here. and it tells you the resolution, and you can click on it. And when you do, it shows you temperature with time, precipitation with time, wind and pressure, cloud cover, etc., in kind of a little bit more of a point forecast format.
Awesome. We have another live question from Annie and Toria. You guys can unmute yourselves. Yep.
We are back with kind of a different question. Ethan, I saw the beautiful picture of that crown on your computer, and it's something I've been thinking about, is just assessing hang fire. And I know as forecasters, you all are going in to get up to crowns and look at them and yeah, just study them. And so I'm curious if you can talk a little bit about that sort of decision making of being like, okay, we're going to go underneath this crown, and then sort of how that would maybe translate to us non-forecasters if, you know, there was an avalanche. I feel like we're always like, assess the hang fire and then go. And it's like, well, what does that even mean? So you can also totally punt that question, since it has very little to do with weather.
No, it's a great, we're here to talk about avalanches and weather. So yeah, that's an interesting point. I mean, I think from a personal level, it would really depend on the circumstance, like pretty greatly, as to whether I would make a personal decision to risk myself to go into a potentially hazardous area. Actually assessing hang fire with any reliability, you'd need to be able to see the start zones. And if the start zone is a complex area, you can't really make any assessment with any certainty that you're not putting yourself into an area where there's potential for another avalanche. Also, a clue kind of going in would be if there were natural avalanches. I mean, was it a triggered avalanche and you're kind of coming down, but you hadn't seen any natural avalanches all day? I'd feel a little bit more comfortable being down there if I had to be, than if it was a day where there were natural avalanches coming down to that elevation all day, particularly if I can't see what's above me. And I mean, from a forecasting point of view, we never make a decision to put ourselves in those situations, because no information is worth the risk.
Yeah, a couple of things I'd throw in there. And it sounds like you're asking kind of from like an avalanche rescue perspective. It's pretty unlikely for like hang fire to release naturally, unless like you're continuing to get loading, you know, like, so bringing it back to weather, if it's like continuing to snow, continuing to blow, and hang fire is getting loaded, then you're probably gonna be a lot more concerned than just under kind of static conditions. It's not very common for that hang fire to release naturally. I think where hang fire is a bigger issue in rescue, and particularly for skiers who might be coming from the top of a slope and trying to get down to the crown, as opposed to sledders who are often at the base of the slope. If you come in and you know, drop into that hang fire, it's very likely that you're going to trigger that and potentially bury somebody more deeply. Or I remember an incident in California years ago where somebody went for a ride in an avalanche. Some other skiers dropped into the hang fire. Another skier went for a ride in the hang fire and broke his leg, and it just made the situation worse. So I think the hang fire is probably a bigger concern, just trying to safely access the crown from above, if that makes sense.
Yeah, that was really helpful. Thank you.
Thanks you guys for that live question. One more from the Q&A. We have a great question, probably not an easy one, but is climate change altering the jet stream?
Yeah, I I don't have the expertise to talk to climate as much. I mean, I just have to speculate that it almost certainly has to be. And the reason I would say that is just because the difference, I mean, the jet stream really does align itself with the boundary between the colder pool of air and the warmer pool of air. And also jet streams are more active and stronger when that gradient is stronger. So as for the like specifics on, does it shift the jet stream this way or that way, or do we see it diving further or more sharply? I can't really speak to the exact characteristics of it, but I'd have to imagine that if you change the recipe of the underlying basis of the jet stream, which is the temperature gradient, then you're almost certainly going to have an effect on the jet stream. And I'm sure some of that is talked about in these recent papers linking more active storm patterns or more intense storm patterns, which likely means that the jet stream is diving further south to climate change impacts.
Cool. We're going to wrap this up in another 5 or 10 minutes or so. So if you have any other questions, feel free to chime in here. Maybe in the meantime, Ethan, one question I was thinking of was just about, and we didn't talk too much about winds in this talk, or the wind. I think we all know that, it's kind of related to the direction the storm's coming from. It's driven by, a lot of topographic factors. But is there anything more you'd add to that? Like any other factors that can dictate whether we have sort of a strong wind event, or, why the heck do the soldiers get such strong winds?
Is that really the underlying base question?
All related.
Yeah. I mean, wind is really driven across temperature pressure gradients, similar to why the jet stream aligns itself it is why the jet stream aligns itself between pockets of warm and cold air. But there's a lot of terrain effects that can influence wind speeds as well. That get pretty complicated in mountainous terrain. I think the main reason that the soldiers, and we're talking about kind of right here, and the soldiers just get nuked by northwest wind, is that it's one of the highest points. So generally speaking, as you go up in the atmosphere, there's less surface roughness. There's less things to get in your way of wind coming from upstream, and that's certainly true in the soldiers. So that might be one of the main factors. But also there's usually a pretty strong temperature gradient right between, the valley and the mountainous areas above. That could have some effect on it as well. It's also pretty open to the prevailing storm track, which is generally northwest and west. Winds can, if you've driven I-84 in the wintertime, it's usually just howling one direction or the other, because again, there's nothing to really block those winds. As far as wind effects in the mountains, that gets really complicated. I mean, there can be diurnal winds with wind kind of coming down mountains in the nighttime and up mountains during the daytime. There's channeling effects where wind coming across the top of the mountains can be realized as wind actually coming down the valleys a little bit more. That gets shifted. There's all kinds of things going on that are pretty complicated to really pin down as one particular pattern or another.
Well, thanks for that. I kind of threw you an open-ended question there.
That's okay.
Yeah, I got time for another question or two. If anybody wants to throw anything in the chat or in the Q&A, or raise your hand.
Well, thanks everybody for hanging in there, and we really appreciate you guys tuning into these.
Yeah, thank you guys all for attending. Our next Digging Deeper is in the Wednesday in 2 weeks. The topic on that one is kind of to be determined. We're working around some scheduling with potentially getting some guest speakers in. So kind of stay tuned for that one. There'll be a lot of publicity as we get closer and get that one pinned down. If you guys have any topics that you want to know about, or you want us to cover that we haven't covered yet, or you want us to touch on again, drop us a line. Our email is on our website, but it's at info@sawtoothavalanche.com. We'd love to hear some suggestions on what you're wanting to learn about. Otherwise, stay safe, enjoy the rest of your winter, and pray for snow. Thanks so much for coming.